So let's talk about the mean value theorem and Rolle's theorem. I want to talk about the mean value theorem first. Essentially what it says, it's written right here, but it says if a graph is continuous, like you see here, let's just look at the graph for a second. If the graph is continuous and differentiable, so this is a nice polynomial, it looks like it's continuous and it's differentiable. There's no kink in the curve. It would be like a kink in the curve or something like that. It has to be continuous, so it doesn't have a break in the curve either, all right? If it's continuous and differentiable, then if you look at the endpoints of the graph and you find the slope between those two endpoints, then there is at least one point in between those two endpoints where the tangent line has the same slope as those two endpoints. In fact, on this one, it looks like there are two of them. All right, so there's a nice video in the book that explains all this. It doesn't really explain it so much, but it's a nice little animation of it. So let me show it to you. It's right here. It doesn't. So here's the graph, right? And the book. Here we go. So basically, let's stop it. It starts like this, and then if you play it, it'll graph the secant line there. If you play it again, it'll graph a tangent line to the curve, and you hit it again. It follows a tangent line until it stops, and if you notice, the tangent line here will stop whenever it is parallel to the secant line. So apparently, what we're saying here is that you have your endpoints A and B, and then there must be a value C, in between A and B, where the slope of the tangent line is the same as the slope between A and B. All right, so let me pull this away and let's look at the definition actually. So where's the definition? It's right here. So f is continuous on a closed interval. Got that. F is differentiable on the open interval. It's differentiable on the open interval. It says open because you can't take the derivative at the endpoints. And then there's a number c such that, see the slope at the endpoints, this is just m is equal to y2 minus y1 over x2 minus x1. Slope at the endpoints, that is equal to the derivative, the slope of the tangent line, at a certain number c. So there exists a number c. So this is called an existence theorem. It says there exists a number where this is the case, but it doesn't tell you how to find it. All right. So let's do an example of this. Let's see. Here, yeah, this is a good one. All right. So it says verify that G satisfies the hypotheses of the mean value theorem. Yeah, it's continuous and it's differentiable. We talked about that. On interval 0, 8. All right. Estimate the value of C. Values of C that satisfy the conclusion of the mean value theorem. All right, so the conclusion is that there's C such that f prime of C is equal to f of B minus f of A all over B minus A. So what you would do in this problem is you would find the slope. So let me do that in blue. So you'll find the slope manually here. So the slope looks like it's going to be over, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and up 1, 2, 3. 1, 2, 3. So the slope is 3/8. And so now we have to estimate from 0 to 8. All right. So now we say, okay, here is the slope between the endpoint. All right. And now I'm going to try to find the C value where get the same slope as that. And so maybe this one here, there's a C value, let's call that C2, and then this one here, down here, maybe this is C1. And so you work through it by determining if you draw the tangent line there, and then you try to see if this is also 3/8 like that, okay? So that's how you would do that problem. Now if you look at the third part, it says estimate the value, and it changes the interval to 2, 6. So 2, 6 would be a little different slope here. Let's see. So at 2, 2, 6, 8, right here, now we're looking at a line like that. And so the C value will be maybe somewhere like this instead. So that would, this is your C. Well, I can't draw a straight line down. This is C down there. All right, so let's move on to an actual problem. How about this one here? Verify that the function satisfies the hypotheses, the mean value theorem, blah, blah, blah. Let's try 12. 12 seems harder. So let's see here. So 12 is f of x equals x cubed minus 3x plus 2, and we're looking at negative 2 to 2. So the thing that I do is the first thing I do is I find the slope, f of b minus f of a over b minus a. And so this would be f of 2 minus f of negative 2. Note that this is a and this is b, right? And so over, and then b minus a would be 2 minus a minus 2. So f of 2 is, so now we look at what f of 2 is. So we're going to look at what f of x is. So we do f of 2 is, let's see here. So I got 1. All right. So we got 1 out of that. And so that's the slope. So now we have to find the C value that satisfies the derivative of that. So the end of the mean value theorem says f prime of C is equal to f of b minus f of a all over b minus a. So we're going to find the C value for which this slope is 1. So what I'm going to do is I'm going to take the derivative of my function. So f prime of x is 3x squared minus 3. And I'm going to set that equal to, well, I'm going to go ahead and put it in the C. So f prime of C is 3c squared minus 3, and set that equal to 1. Now I solve for C. So when I do that, I get c squared is 4 over 3, so C is plus or minus, I can't draw this, 2 over square root of 3. All right, that's about 2 over 1.7. So now we have to look at this 2 over square root of 3, and we have to compare it to the original interval. So plus or minus 2 over square root of 3. So on a calculator, that gives you about 1.15. So that's plus or minus. So that's definitely in this interval. So both of them apply to C. All right, so what I've done is I've graphed it, and let me pull it over here. And here it is. So this is y equals x cubed minus 3x plus 2. It's on the interval. We're looking at the interval from 2 to negative 2. Let's see there. And then when we draw a line between those two, those are the endpoints. Now the graph continues on, but we don't care about where it continues on. We don't care about any of this. We just care about what's inside between negative 2 and 2. And then, so we got 1.15 as 1.15. So this is like 1.2 there. So apparently right there is one of them. And then negative 1.15. And then right there is the other. And sure enough, these two tangent lines that I'm graphing have, looks like pretty much the same slope as the line, the secant line that ends up between 2 and negative 2 is the slope between the endpoints. All right, so what happens if the endpoints are the same value? All right, so if you look at this graph right here, the endpoints end up, not the endpoints are the same value, but the function values are the same. So if that's the case, then the slope of the tangent line will be 0, because the function values are the same. So there's a tangent line right there that's 0, and there's a tangent line right there that's 0. Now we still need a function that is continuous and differentiable, but this time what we're going to require is that the slope between the endpoints is 0. In other words, by saying that, whenever you have a fraction equal to 0, only the numerator is 0, And so the numerator being 0 would make these two endpoints be equal. So the endpoints aren't equal, but the function values at the endpoints are equal. So I don't know if I have another graph of this, do I? I'll just draw it right here. This is called Rolle's theorem. Rolle's theorem. And so what happens is you have your nice little function. It's moving along. And then the endpoints, at the endpoints, the function values are the same. And so if you draw a line there it's going to be horizontal, well then there's going to be another horizontal line there, and another horizontal line there, another horizontal line there. So it looks like there are going to be three C values here. A C value here, a C value here, and a C value there. We'll say C1, C2, and C3. So there's this number C such that derivative is equal to 0. Now, a lot of times people see this and they're like, well, where is this ever used? There's a good example in the book where they use velocity and stuff. It's actually used to prove a lot of stuff. For example, if you look at this one, like number 20, it says, show that the equation has exactly one real root. Well, so remember a root is where a function is equal to 0. All right, so it's the x value that makes the function 0. So if you had something like x squared minus x, let's see, minus 20 equals 0, then when you factor that, you see that x minus 5 and then x plus 4 equals 0, and you end up getting x equals 5 and negative 4. 5 and negative 4 are the roots. So 5 and negative 4 are roots because when you plug them in, you get 0. So the question here is, what are the, show that this function here has exactly one real root. Well, the same thing, the answer to that is the same thing as the question for that is the same thing as the question for this. Suppose you had y equals x cubed, and you had y equals e to the, sorry, let's say it's y equals negative x cubed, and then y equals e to the x. And you want to find out where they intersect. So good old negative x cubed looks like this. Let me draw it with a different color. And then e to the x looks like this. All right. And so the question is, where do they intersect? Well, it looks like that's negative. And it looks like they only intersect once. Okay. Now we have to prove that they only intersect once. And I know it sounds pedantic. You kind of know that they intersect once if you know what their graphs are. But they're giving you an easier problem. Like it's obvious here, but a lot of times in applications it's not so obvious. So that's why they're asking you to do it for an easier one. Anyway, so what does that have to do with this? Well, by setting them equal, you find out where their intersection is. So you can say e to the x is equal to negative x cubed. Well, let me do it in the other color. You can say negative x cubed equals e to the x. And to find out where they intersect, you set them equal, and then you solve for x. Well, then 0, you move the x cubed over, and so you can make this x cubed plus e to the x equals 0, or like they had it, x cubed plus e to the x equals 0. Okay, so to solve this is the same thing as solving this, which is the same thing as finding out where those two intersect. All right, so back to the question that says, show that the equation has exactly one real root. Well, let's make sure they even have one. All right, so to do that, what you can do is you can say, well, we can use the intermediate value theorem. I can say, okay, well, let's plug in a value here. Let's plug in like negative 1. So so the idea here is we have an idea of where the root might be. So let's plug in like negative 1. All right, so let's see, f of negative 1 is negative 1 plus e to the negative 1, which is, on the calculator, negative 0.63. And now, how about f of 0? F of 0 is 0 cubed plus e to the 0, which is 1, So look, it changes sign. So by the intermediate value theorem, remember that one, the intermediate value theorem, there must be a number where, so since it changes sign, somewhere in between 0 and -1, so f of x changes sign in here, changes sign. So somewhere in there, f of x must be equal to 0 in the interval. Because in order to change sign, it has to be. Now, here's the thing though. These have to be continuous, right? So, like, for example, you could have a function that changes sign all right, but it's not continuous. It's positive here, and then it's negative down here, right? It's negative down there. But the idea is that if they're continuous and it changes sign, it has to hit 0 at some point. Well, how do I know that this is continuous? Well, it's the sum of two continuous functions. An exponential function is continuous and a polynomial is continuous. And the sum of two continuous functions is continuous itself. All right, so we have that. All right, now that we know that it has at least one root, the question is, it says, show that it has exactly one root, okay? So what I'm going to do is I'm going to prove this by contradiction, by saying, well, maybe they have two, okay? So suppose, by contradiction, let's call them A and B. Call them A and B, okay? So then, since I call them A and B, so f of A must be equal to 0, and f of B must be equal to 0. Now, one of these is probably in this interval, right? Okay, so f of A is equal to 0 and f of B equal to 0. Well, you can use Rolle's theorem here. Rolle's theorem says, hey, look, the endpoints, at the endpoints, they have the same value. So basically, what I can do is I can use the end of Rolle's theorem. So Rolle's theorem says, if f of A is equal to f of B, then, and f is continuous and differentiable, then there is a C in AB such that, ST, such that f prime of C is equal to 0. Well, let's see. So let's go back up to the function. So here is the function. This is the function right here, x cubed plus e to the x, right here. That's my function. So I'm going to say that. All right, let's see. So then f prime of C, f prime of x is 3x squared plus e to the x, because the derivative of e to the x is e to the x. And so there's got to be a C value such that that's equal to 0. Well, the problem is this is always positive, and e to the x is always positive, because 3x squared is a parabola, and e to the x looks like this. It's always positive. So this can never happen. No way. So since that can never happen, the assumption that there are two roots doesn't hold at all. All right.